Welcome to 5.2 line integrals. There's a lot of words and a lot of and diagrams in here. I probably should not have had this many diagrams and words in one page. I should have probably talked them through and draw the pictures by myself, but whatever. It's good lesson planning, so deal with it. Anyways, line integrals. What are line integrals? You've done double integrals. You've done single integrals first before. Single integral, area under the curve, right? Double integrals is the volume under the surface or the mass of an object, mass of a disk, a thin disk, with density function, whatever, right? With a density function. And triple integrals, you can also use that same idea with the mass and the density. It also works. What is a line integral? A line integral is a little bit more strange, I guess you could say. Um, it has to do with vectors. So I'm gonna take these two diagrams for example. Line integrals, in this case, there's two types of line integrals. I'm gonna talk about the one for work and the one for flux. And we're gonna do the one for flux in 5.4. Right now we're gonna do the one for work. So the line integral for work is when there is a vector field, a force field, or whatever. In this case, it's a gravitational field, and the vector field is going to point in a direction, right? It might be velocity, it might be charge, whatever. The vector field is going to point in a direction. If the box or if whatever your entity is moving in that direction, that same direction that the vector field is pointing, then the vector field is doing work on that box or what on that object. So that's what it means to do work. So when the box falls in the direction of the box's when the box falls in the direction of Earth, I don't even know what I wrote here. The box's path agrees with the gravitational field, so the gravitational field has an impact, so it has done work on the box. However, in B, when the box moves in a direction, in this case it's circular, it's completely perpendicular. At every point right here, you can see that this is perpendicular, 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 normal. The field has done no work on the box. There's no work done, so therefore, or no, it doesn't agree with the field at all. It moves completely perpendicular to the field, so the field has done no work on the box. All right. So I'm gonna introduce you with a definition first, because these line integrals work best when it is a what do you call it? Yeah, these line integrals work best when it is a piecewise smooth curve. A piecewise smooth curve is what? A piecewise smooth curve are these. They're smooth, so they're continuous and differentiable, but they're piecewise smooth, so they can be you can separate them into certain curves that are continuous and differentiable. What wouldn't be a piecewise smooth curve? This wouldn't be a piecewise smooth curve with asymptotes. That's strange. That's not continuous. I mean, you could say that it's continuous, but it's not continuous because it goes all the way to infinity, and we don't. That's just foul. That's so weird. And if it has holes, that's not piecewise smooth. Um, this is, however, actually, if it has holes, it might still be piecewise smooth. Depends on how you define it. But this is definitely this is piecewise smooth, even though it looks like it has a bunch of sharp edges, not differentiable. But you can say that each of those lines that I drew that weren't sharp edges, they are a piecewise function. So it's piecewise smooth because you can have 17 different piecewise functions that are continuous and differentiable, even though the entire thing isn't continuous and differentiable. Um, yeah, so that's what piecewise smooth means. Now, okay, the work on a box from a gravitational field that is constant like this can be, I don't even know what I'm supposed to put in here, but can be determined, I guess. by this formula right here. So as you can see, you go in the R. If you go in this direction right here, this direction is not agreeing with the direction of gravitational or with a force field, with a red force field, right? The force field is red. Let's say the force field is red, and the box is moving from that point, from the left to the right, like that. It's not agreeing completely. It's not agreeing completely with the direction. However, it's still agreeing slightly. It's still agreeing with um, it's still agreeing specifically this much. That's how much it's agreeing, right? That like this is how much it's agreeing. Now, if you I think you can see that this R function that it's not a function. I'm sorry. This R path right here is definitely longer than the blue path. The R path is definitely longer than the blue path, so it's not agreeing completely. That means the work done on the box is not R. It's not the length of R. It's not going to be that. It's instead going to be the blue. So if it's the blue, then what is that? What is the blue? The blue is, well, if I put theta here, right? And then this is, let's say this is the actual, this is the, let's say this is x, right? So if this is x, then the cosine of the angle will be equal to uh, the absolute value or the magnitude of x divided by the magnitude of r. So the magnitude of x is r cosine theta. And work is equal to force times, well, the most basic formula of work is equal to force times distance. But the vector form of the formula of work is force dot product with the radius. The force vector dot product with the radius vector. And if you watch 1.1, if you guys don't remember, you can go watch 1.1. The force times the radius, or the force dot product with the radius, is equal to the magnitude of force times magnitude of the radius times the cosine in between them. So that's why we get this r cosine theta right here. So it's the force times r cosine theta. Now in this case, they're all constant. So the product is just this right here. The force times the radius, magnitude of force times the magnitude of radius times cosine theta. However, not all fields are like this. Of course, fields change, and of course, paths change. So we're going to have to, sometimes we're going to have to deal with when the paths change like that, right? Force field's constant, paths change. Still actually quite easy as long as you find a parameterization for the path, you would be able to do this, but it's a little bit harder because the path is no longer straight, so you can't just do a simple physics 1 calculation like this. This in this region, or in this perspective, what you're gonna get is, well, you're gonna have to calculate the contribution of every single point of work instead. So you're gonna have to calculate, yeah. So as every single point gets smaller and smaller and smaller, you're gonna have to calculate all of those points and add all of them up to form a line. So if you say, well, this is this small point right, this small point right here, and if you zoom that in, it's gonna look something like this, right? And this is nearly straight. This is nearly straight. So what you're gonna get is, well, because it's nearly straight, we can assume that it's straight. As we get smaller and smaller, it's definitely going to be straight. So if it's like this, then the angle in between them is, let's say, theta I, right? The reason why I'm putting I is because every single, I'm sorry, this is wrong. This is wrong. It's the sum, right? So it's the limit as I approaches infinity of the sum, like that. All right. Anyways, so you're going to add up all of the theta i's times delta r i's, because the delta r is going to change every time, and the theta is going to change every time. In this, yeah, so the theta, because of the path, theta and delta r is going to change every time, and they don't necessarily have to be equal lengths either. But yes, so if you combine them together, you will get, well, now it becomes f dot ri. So limit as I approaches infinity, that means limit as we add up infinitely many of those small paths, of these small blue paths right here, and we zoom them in so that they become like constant paths, but they're not really constant paths. Um, but the closer and closer we zoom in, the closer it will become a constant path. So we add up all of the small work contributions from each of those paths, and this is what we end up with. We will end up with the integral along the path C of f dot dr. That's what delta r is going to turn into, and I should do delta ri rather than just ri. That's wrong. Yeah, my examples suck. How do we evaluate this f dot dr? So this is how we evaluate the f.dr. Looks very confusing, of course, but we are going to work through an example. It's not very confusing. There's two ways to evaluate it. I like my way better, but you can also use the other way. They're pretty much the exact same way if you understand what this is. But so what I do is I do f.dr right here, right? F usually, if it's a two-dimensional function, usually it is mn, right? So this is a two-dimensional vector field dot with a two-dimensional curve. Mn dot dr, the change in r is a change in x and a change in y, right? So the change in r is if you add the change in x, and if you add the change in x, and then if you add a change in y, then you get the change in r. Makes sense? Yeah, so that's what dr is. So it's dx dy is equal to the integral of mdx plus ndy. Now we have to parameterize the path. Why do we parameterize the path? Because this is strange. Have you ever evaluated an integral where m and n can both be functions of x and y, but there's two differentials in the thing, in the function, in the integrand? Probably not. So we want to make it so that it's one differential instead. So we have to parameterize x and y in terms of one path. Sometimes it'll be theta, sometimes I'll use theta, but most of the times I'll use t. So if x is x as a function of t and y is y as a function of t, then dx is x prime of t dt, and dy is y prime of t dt. So mdx and ndy, right? Mdx plus ndy becomes m of xy, and they're both functions of t, times dx, which is this. So this is where the dx comes from. This is the dy, and this is n. So m dx plus n dy. And you can factor dt out to get you this. Looks very confusing, but we'll be able to do it. How do we find the bounds? We'll make a parameterization, and then we'll try to find the bounds that way. So find the work of the force field. F is xi hat minus yj hat, given that the path is a quarter circle beginning at a positive x-axis, ending in a positive y-axis with radius 1. So what's the parameterization? Well, first of all, let's calculate what m dx plus n dy is. So the integral along the path C of f dot dr is equal to the integral of m dx plus n dy. All right. So what's x? What we want to when we want to parameterize this, usually we want to parameterize it in terms of the path, right? So in this case, what I'll use theta, because the path is a circle, and the best parameterizations for a circle is x equals cosine theta. and y equals sine theta. Why am I using cosine theta instead of r cosine theta, which is what we use for polar? Because the radius is only 1, right? It's because the radius is only 1, it's always constant, so we're not going to use r because the radius doesn't change. So what does this give you? This gives you dx is minus sine theta d theta. That's ugly as heck, d theta. And then y, or dy, is cosine theta d theta. And let me actually write out the x and the y. So this is xi minus yj. So it's x dx minus y dy. So what does this end up being? This ends up being equal to negative sine theta cosine theta minus sine theta cosine theta all d theta. How do I end up with that? Well, m is x. So what's x? X is cosine theta. It's cosine theta right here. Dx is negative sine theta, so negative sine theta right here. And then d theta I already factored out. Y is sine theta right here. Dy is cosine theta d theta, cosine theta d theta. So what do I end up getting? Well, first of all, let's decide the bounds. So where does this start? This start at 0, so the bound is 0, right? There's cosine theta and sine theta. We're not changing direction. We're not doing anything crazy. The cosine theta just starts at 0 because that's where the point is 1, 0, and then it ends at 0, 1, which is pi over 2. So pi over 2. If you put pi over 2 here, cosine pi over 2, 0, sine pi over 2, 1. So the integral from 0 to 2 of this. So this is equal to the integral from 0 to 2, or 0 to pi over 2, of negative 2 sine theta cosine theta d theta. So what does it end up being? This ends up being, I want to use a trig identity. I really want to use the trig identity. I'm going to use the trig identity. 2 sine theta cosine theta. You can do a u substitution. You can do sine theta equals u, cosine theta d theta equals, reverse chain rule. Sine theta is u, and du is cosine theta d theta. You can do that as well, but I'm not going to do that. I'm going to do I'm going to turn this into a sine 2 theta situation. Negative sine 2 theta. This is the identity that I'm using. It's 2 sine theta cosine theta equals sine 2 theta. What will this give you? This will give you 1/2 integral evaluates to negative 1/2 cosine, or no, actually positive 1/2 cosine, because negative sine evaluates positive cosine. Positive 1/2 cosine theta evaluated from 0 to pi over 2. So at pi over 2, that's 1/2 cosine of pi, which is negative 1/2. And then minus 1/2 cosine at 0, which is 1/2. So negative 1 is the answer to this question. Now, what if we evaluated the other direction? So let's evaluate it the other direction. That was a lot of work. That looked like a lot. To me, that was a lot of work. So let's evaluate it the other direction. How do we evaluate it the other direction? It's a little bit harder to decide the parameterization, but the trick is actually to just switch the sines and cosines. So now x is sine theta and y is cosine theta. So why does that work? Let me move this a little bit right here. Move this right here. So if the x is sine theta, this is still really messy. Still really, really messy. All right, let's actually just close. Yeah, just right there, right there, right there. I hope you guys can still see that. All right. So x is equal to sine theta, y is equal to cosine theta. Why does that work? We can keep the same bounds actually. So at theta equals 0, y is equal to 0. I'm sorry. At theta equals 0, x is 0, and y is 1. Right? That works with the 0 case. At pi over 2, sine of pi over 2 is 1, and cosine pi over 2, 0. Right? And to be sure, we'll put one more step. To be sure, we'll have one more step. So pi over 4. So at pi over 4, which means like halfway between 0 and pi over 2, at that point, you'll have square root of 2 over 2, square root of 2 over 2. So yeah, it works. It goes from this direction to this direction. From here at 0 to here at pi over 4, and here at pi over 2. So what are we going to end up with? We're going to end up with dx is now cosine theta d theta, and dy is now negative sine theta d theta. Which means what? Which means you'll get the integral from 0 to pi over 2 of x dx sine theta cosine theta minus y dy plus sine theta cosine theta, because minus and negative, minus y dy and minus again d theta. So this will give you the integral from 0 to pi over 2 of 2 sine theta cosine theta d theta, which will give you the integral from 0 to pi over 2 of sine 2 theta d theta, which is equal to negative 1/2 cosine 2 theta evaluated from 0 to pi over 2, which is 1/2 minus 1/2, which is 1. If that was a little bit fast, I'm sorry. Slow down the video. But what do we notice? We notice that if you go the other direction, it's not negative 1, it's 1. So that's actually a very good thing to point out. The thing to point out is if you do a line integral to the in the forward direction, and then you do a line integral again in the backward direction, you're gonna get opposites. You're gonna get opposite values. So that's a good fact. I hope that you will internalize, because that becomes important later. All right, let's evaluate more line integrals. F.dr right here. I'm gonna show you another way to evaluate these integrals. Same methodology, but just in a little bit more condensed form. I think you guys will like this more, but I like mdx plus ndy more. So evaluate this. If f is this moving along the arc of a cycloid, t minus sine t, 1 minus cosine t. So they already parameterized it for us. There's r of t. So what can we do? All we have to do is we just have to plug f of r of t. F of r of t. And if you notice what this is right here, dx and dy, dx and dy is technically just the derivatives of the parameterization. See? It's just the derivatives of the parameterization. So you can actually multiply by, this is your parameterization, so you can multiply by the derivative of the parameterization, dt. So this is equivalent, right? mdx plus ndy is equal to this. It's the same thing. It's just a little bit different of a notation. So our parameterization is here. The derivative of parameterization is here. Our parameterization is right here. And the derivative of it is right here, right? Our parameterization right here, derivative right here. It's the same thing. It's just this is a little bit more condensed. And it's basically we haven't done the dot product yet. Once we figure out what the vectors are, we will do the dot product. So let's just do this. Ready? Equal to integral. We're gonna say this is one arc, the arc of one cycloid. So the arc of one cycloid, a cycloid looks like this. This is the path of a cycloid. It's like that. So the arc of one cycloid is the time it takes for the not the x but the y to go to 0 again, to go to 0 twice. Or yeah, to go from 0 to 0, from valley to valley. I guess you could say. So what's that time? That time is, if you put 0 in cosine t, you'll get 1. So that is from 0, t equals 0, to when's the next time it's 0, or when is the next time cosine t is 1? It's 2 pi. So it's 0 to 2 pi. It's a little bit harder. 0 to 2 pi. F of r of t. What is f of r of t? It's well, if you write this in notation form, f is equal to x y plus 2, right? So f of r of t is just whatever we have right here in r of t, t minus sine t. So everything that you see on the left, you replace with x, and everything that you see on the right, you replace with y. And then 1 minus cosine t plus 2. So it ends up being 3 minus cosine t. So this is t minus sine t. Actually, I'm just gonna do the multiplication later. This is it gonna be really annoying. What's r prime? R prime is 1 minus cosine 1 minus? Yeah, 1 minus cosine t. I was confused for a second. I shouldn't have been. And then positive sine t. So what's 1 minus cosine t plus 2? It's 3 minus cosine t. All right, let's dot product. So t minus sine t times 1 minus cosine t is what? T minus sine t times 1 minus cosine t is, we have t minus sine t minus t cosine t plus sine t cosine t. That's messy. That's very messy. All right, what's 3 minus cosine t times sine t? That is plus 3 sine t minus sine t cosine t. So what cancels out? This cancels out, this cancels out, and 3 sine t minus sine t is 2 sine t. So you'll end up getting t plus 2 sine t minus t cosine t dt. All right. That's messy. That's very messy. In fact, I'm going to this has to be done with integration by parts. So that's going to be a challenge. I'm going to do that first, actually, because these two are easy. These two you can do by yourself. But this is integration by parts, which I don't know if you guys remember. So t cosine t, you have u dv is equal to uv times uv minus v du, the integral v du. So ultraviolet voodoo is a pretty good mnemonic, I guess. So u is t, and dv is cosine t. So u dv is equal to uv t sine t minus v du. What's v du? It's just the integral of sine t dt. Oh, what's the integral of sine t is minus cosine t, so it's t sine t plus cosine t. There you go. So that's what the integral of t cosine t is. So what you're going to end up with, this is equal to, I'm pretty sure that's still in the page. Okay, the integral is in the page. That's all we need. 0 to 2 pi of t squared over 2. Or, no, I'm sorry. This is equal to t squared over 2 plus 2 sine t, but it's plus is gone now, so it's 2 minus 2 cosine t, because the integral of sine t is negative cosine t, minus t cosine t, so minus t sine t minus cosine t, and we don't need the plus c because it's a definite integral, 0 to 2 pi, which is equal to what? So 2 pi squared, that's just pi squared, or 2 pi squared is 4 pi squared, and then divide by 2 is 2 pi squared. Minus 2 cosine, what's cosine 2 pi? Cosine 2 pi is 2. And t sine 2 pi, sine 2 pi is 0, and then minus cosine 2 pi again, which is 1. All right, minus at 0, t squared over 2, that's just 0, minus 2 cosine 0 is 1, or I'm sorry, 2 cosine 0 is 2, and minus 1. So we have 2 pi squared minus 2 minus 1 minus 0 minus 2 minus 1. That's 2 pi squared. That's your final answer. All right, so the line integrals, they're pretty interesting to evaluate. They're not very hard, or they're just kind of, if you algorithmically do it, it's not very hard. If they don't give you the parameterization, it's a little bit harder to figure out, but you can definitely do it. So I think the next one's the physics. Nope, it's not. Okay. This one, you have to find the parameterization. So how do you find the parameterization for this one? It says the particle that moves from a straight line. In this case, there's three functions, three whole functions. So we can use this, but in 3D, we don't use m and n. We actually use f is pqr. F is equal to pqr. Why? I don't know. I really don't know. But we can parameterize all of this because we know what straight lines are. We know how to make straight lines from 1.3. Equations of lines. We need a direction vector, a vector that indicates the direction, like a slope, and we need a starting point. And the starting point, we can use 0, 1, 2. What's our direction vector? How do we figure out what our direction vector is? We can take the right point and subtract the left point. That's our direction vector. Pretty simple. And we can actually take like any parallel direction vector as well. So it doesn't have to be just the direction vector that we create. It can be any parallel, but then it'll be a little bit confusing because your bounds will be a little bit tougher. Anyways, so if we start from 0, 1, 2, what do we get? So what is our direction vector? First of all, I'm going to say the direction vector is d. And the direction vector is, well, -2, -1, 0, minus 0, 1, 2, which is -2, -2, -2. Okay, it's -2, -2, -2. So what does that mean? That means the equation is x. The equation is x is equal to 0 minus 2t, y is equal to 1 minus 2t, and z is equal to 2 minus 2t. And that's your parameterization. It's very nice because we already know what the equation of a line is. We can just make the parameterization like that. They're all in terms of t. They all, they all define a line. And that would make dx, dy, and dz even easier to calculate because they're all 2, right? Dx is -2 dt. Dy is -2 dt. And dz is -2 dt. So they're all -2. So everything will basically just multiply by -2. Now what are our bounds? So what are our bounds in this case? So first of all, let me actually just put the integral. So the integral is the integral of what are the bounds? So I'm going to leave the bounds blank first of all. X minus y squared. Minus 2t minus 1 minus 2t squared. That's actually very messy. This is going to be very messy. Right? And then plus what? Plus 1 minus 2t minus 2 minus 2t squared plus 2 minus 2t minus 2t squared, or minus 2t squared. So it's so disgusting. It's such a disgusting function. It really is. All right, put all the parentheses you need, dt. All right. So I'm not gonna waste your time. I'm just gonna calculate these really quickly. So 1 minus 2t is 4t squared minus 4t minus 1. This is 4t squared minus 4t minus 1. So what you'll end up with is the integral of negative 4t squared, and then minus 4t plus 2, or minus 4t minus 2t is plus 2t, and then minus 1 is plus 1. Actually, no, this is supposed to be plus 1. I don't know what I was talking about. Minus 1. Minus 1. 1 minus 2t is 1 minus 2t. 2 minus 2t is 4 minus 8t plus 4t squared. So 1 minus 4 is minus 3. Minus 3. What else? Minus 2t minus 8t is plus 6t. And plus 4t squared is just minus 4t squared. So they'll all be there. They will all be minus 4t squared. Plus 2 minus 2t. So minus 2t squared is just 4t squared. So this is very simple. It's just 2 minus 2t minus 4t squared. And I forgot to do this, so I should have done it. But we have to multiply everything by minus 2t as well, because that's our d, or minus 2, not minus 2t. So I can actually just put it outside. Minus 2 dt. Dt. All right, let's combine like terms. The integral of negative 4t, negative 4t, negative 4t. So that's negative 12t squared. Plus 2t plus 6t minus 2t is plus 6t. Minus 1 minus 3 plus 2 is minus 2. Minus 1 minus 3 plus 2, yeah, minus 2. Dt. Okay, what are our bounds? We actually got to calculate the bounds now. Very important. The bounds are, well, if we set our original function or point at 0, 1, 2, then that's where the time doesn't exist. That's where the time doesn't matter. Or, well, actually, the time does matter. The time's at 0 at that point, right? Because that's our point. That's our point right there. When the time doesn't exist, or when the time doesn't affect these x, y, and z coordinates, they're all 0. It becomes 0, 1, and 2, right? And when the time is 1, which is what we've set basically for this equation, it will become negative 2, negative 1, and 0. So the bounds are from 0 to 1. So what does this mean? This means that it's negative 2, open parentheses, negative 4t cubed plus 3t squared minus 2t. That's so nice. That 4, 3, and 2 downfall, that's so nice. From 1 to 0. 0 will get you nothing, but this is equal to minus 2 times minus 4 plus 3 minus 2, which is 6. And that's the value of the line integral. That is that's some art right there. The 4, 3, and 2. Anyways, let's not talk about that. So you guys can finish the video right now, unless you want to watch this physics example as well. I think it's a little bit useful because this chapter there's a lot of it based on physics. So this is a pretty useful example as well. Find the force of the particle at time t if the mass is m, capital M. So if you know the Newton's second law says that the force at time t is equal to the mass scalar quantity. So I'm just going to use m because the mass is m, times the acceleration at time t. What's the acceleration? The acceleration is in chapter 13 also the double derivative, or the second time derivative of the position. Sometimes you'll also see it like this, or just without the hat at all, and just 2 dots on top. That's the time derivative, right? The time derivative gives you dots. Second derivative, 2 dots. First derivative, 1 dot. Time derivative, you have dots on top. But if it's any other derivative, then doing ddt or ddx is more safe. Anyways, what's the acceleration? The acceleration is a double derivative of r double prime of t, which you guys can calculate by yourself. I'll give you 3 seconds. 3, 2, 1. All right, it's 12 minus 12t squared. Or it's 12, 0, and minus 12t squared. Why is there a 0 here? Because it's I hat and k hat, not j hat. So it doesn't move in the y direction. It just moves in the xz direction. xz plane? Yeah, xz plane. So 12, 0 minus 12t squared. So what does this mean? This means that f of t, in this case, we don't have to do f of r of t. Why? Because f of r of t doesn't, like, there's r of t, but f is a function of r of t already. F is a function of r of t. How? F is a function of r of t by f of r double prime of t is equal to m times r double prime of t. So that is our function already. So that's why we don't need f of r of t. F is already in terms of t if we find a. So it doesn't matter. So what does this end up being? This ends up being f of t is equal to 12, 0, or m times 12, 0. I don't know why I'm doing parentheses. Minus 12t squared. So that's the force of the particle at time t if the mass is m. So what's the work? What's the work of the particle at time, or during the time interval from 0 to 3? The formula is f of r of t, right? So f dot dr is equal to f of r of t dot r prime of t, but we already have f of t, right? So it's basically, it's just f dot r. F dot r, f dot delta r. I'm sorry, not f dot r. F dot delta r, right? So the change in r. F, we already have. What's the change in r? Change in r, with respect to the change in r, dr is equal to r prime of t dt. So it's just r prime, right? So it's f of t dot r of t. Or r prime, I'm sorry, t. What's r prime? We need to calculate r prime. We're going to put it up here. R prime is 12t 0 minus 3 or 4t to the third power. So f of t dot r of t dt, and t is 0 to 3 because we already have that given to us. That's equal to what? That's equal to 0 from 0 to 3 of 12t times 12 is 144t. And negative 4t cubed times negative 12t squared is 48t to the 5th power dt, which is equal to 72t squared plus 8t to the 6th power from 0 to 3, which is equal to a massive number, a huge number. It's done a lot of work. 72 times 3 squared plus 8 times 3 to the 6th. I don't even know how much that is. That's 3 to the 4th plus 3 squared. So it's like 10, I think. Wait, no, it's 90. So that's equal to what? That's equal to, I'm gonna simplify this kind of a smart way. 72 times 3 squared plus 72 times 3 to the 4th, which is equal to 72 times 3 squared times 10, which is 5, or no, 72 times 9 is 648, so 6,480. And that's the line integral. That's a big number. Very, very big number. But sometimes force fields are like that. They give you big numbers. It's not just 6,480, I'm sorry. It's m times 6,480. So I missed the m. So I need to put the m in here. M is not as a function of time, right? It's a mass. It's just, it doesn't move as a function of time. Um, so this is m times this. So it's m times this. So it's m times this, right? So if the mass is not a very big mass, then it's not going to be a lot of power or a lot of energy. But if it's a lot of, or a lot of work, I guess I should say. But if it is a huge mass, then it will be a lot of work. That's gonna be it for today's episode. It's gone on for probably too long, but I will see you next time.